Hey, everybody, here's your notes for 7.1. This is an introduction to exponential functions. Okay. This year, we've spent a lot of time talking about polynomial functions. I've got an example on the left there. Polynomial functions can have one or more terms in them, and they have exponents larger than 1, x squared, x cubed, x to the fourth, sometimes lots of those terms. So there's an example on the left. We went from polynomial functions to rational functions, which is basically a polynomial function over another polynomial function. Okay. And we saw all kinds of crazy looking rational functions. And then here's an example on the right of an exponential function. Generally a lot simpler looking, both in the algebra and in the graph, than polynomial functions or rational functions. Even though polynomial and rational functions can be fairly simple, they can also get very, very complicated. Exponential functions, not so much. Before we talk about the details of the algebra and the graphs, I just want to mention some examples in real life where these types of mathematical equations are necessary to know and understand in order to do work in certain areas. For polynomial functions, far and away the most common example is for what we call projectile motion, that is, objects that are flying through the air. And we need to understand quadratic functions to be able to study things that are flying through the air. Examples of rational functions, gravitational pull. If you study that in physics one of these days, that is a rational function, or lots of equations involving electronics and magnetism can be studied through rational functions. Exponential functions is probably the one that's going to touch the most of you in the most significant way in your life, in the sense that, let's talk about what we need to understand about, or what kinds of examples exponential functions represent. Monetary values, things that are going up in value or things that are going down in value. We need to understand exponential functions to study those things, or populations as they're going up or going down, or diseases like COVID-19 can be modeled very effectively and studied very carefully with exponential functions. Just about every one of you is either going to be borrowing money at some point in your life at interest, paying it back at interest, or investing money, okay, which you hope will grow at a certain rate of interest. And very often we're doing both at the same time. So understanding exponential functions and the behavior of exponential functions is really very important. So anyway, let's get into some of the general characteristics of exponential functions, then we'll look at a couple specifically. Exponential functions do have a horizontal asymptote like rational functions often do. We can see in this example over here that this exponential function seems to have a horizontal asymptote at 0. I can't remember. Judging by the graph is always a little subject to error, right? We can't tell if that graph really ever touches the x-axis or if it just gets really close to it but doesn't ever touch it. But it looks like maybe there's a horizontal asymptote at y equals 0 there. Exponential functions do not have vertical asymptotes. This looks like it might. I mean, this rational function over here has a vertical asymptote. I don't know why my pen stopped writing. But it has a vertical asymptote right there at x equals 3. It has another vertical asymptote there at x equals -4. But exponential functions do not have vertical asymptotes. Okay? Exponential functions basically come in two kinds, what we call growth functions and decay functions. If your money is increasing in value, or if some object you own, like a house or a car, is increasing in value over time, we would model that mathematically, the behavior of that increase, with what we call a growth function, an exponential growth function. And if the value is decreasing over time, as so many things do, we'd model that with what we call a decay function. Okay. Parent functions for exponential functions basically look like this here. F of x is equal to some base value to the xth power. And this is the key to exponential functions, is that the input variable, the x, or whatever we call that input variable, very often we call it a t for time. Time is the input variable. Whatever we call it, that input variable is in the exponent position of the equation. This is different from your polynomial functions, where see your x, or your input variable, was the base and your exponents were hard numbers, actual numbers. Okay, so that's the key difference. In exponential functions, the variable is in the exponent position. Right? And then we need some number, some actual hard number to occupy the base. We call that value b. Okay, that's not really a variable. That b there is just saying that that base number can start out being whatever we want it to be. Generally, in real world applications, that value of b is usually between 1 and 2 for things that are growing, and it's between 0 and 1 for things that are decreasing, whether it's monetary value decreasing or a population level decreasing. Then that b value is going to be something between 0 and 1. Now, I say usually because the b value can be larger than 2. It can be as large as we want it to be, 3, 4, 100, a billion. But again, in the real world, usually somewhere between 1 and 2. Towards the end of this unit, we're going to spend quite a bit of time on a very particular real-world application of exponential functions, and the b value is going to be somewhere close to 1, but a little bit larger than 1. 1.03, 1.05, 1.1 maybe. Numbers pretty close to 1, but slightly bigger. Okay, so let's look at two specific exponential functions. And for each one, we're going to answer 9 questions. Now, a lot of these questions you could answer. You could go do the homework assignment and correctly answer a lot of these types of homework questions about these exponential functions without ever having watched this video or listened to anybody talk about exponential functions. Because you've already learned a lot about analyzing graphs and answering questions about things like domain and range and x and y intercept. And you don't need any more special knowledge to do some of these things with exponential functions, but a few of them you do. So this is going to go fairly quickly here. First of all, first question, and I've got 9 questions for each. In the homework assignment tonight, there are 18 questions about the graph of an exponential function. There's 9 questions about one function. There's 9 more questions about another. You're going to be answering all of these 9 questions that I have here. Okay, the exact same kinds of questions. So 9 questions for one function, 9 for another. And then there's 2 questions at the end, which we'll see examples of at the end of this lesson here. All right, so I don't know what order you're going to get these questions in. They could come in random order here when you do the homework assignment tonight, but these are the 9 types of questions. First question, is this function that we're looking at, f of x equals 2 to the x, so I'm choosing a b value of 2 here. Okay, is this a growth function or is it a decay function? So as x gets larger and larger, or oftentimes we say over time, as time moves forward, what's happening to the y values of these functions, of this function? Are they getting bigger, growing, or are they getting smaller, decaying? Clearly, these y values are getting larger and larger and larger. This is a growth function. This is an incredibly simple question to answer once you understand what's being asked. Simply, are the y values getting larger as we move to the right, or are the y values getting smaller? Okay, so these y values are getting larger. This would be a growth function. Just trying to get my pen to turn back on so I can circle the word growth. Okay, what is the growth or decay factor? Okay, factor. This word, if we're talking about factors of 12, we're asking What are things that multiply together to give you 12? A factor is something that is multiplied by other things. Okay. Well, if we're talking about f of x being 2 to the x, if we put in 1 for x, that's 2 to the first. If we put in 2 for x, that's 2 squared. If we put in 3 for x, that's 2 cubed. And another way of writing all of those values, 2 to the first is just 2, 2 squared is 2 times 2, 2 cubed is 2 times 2 times 2. You can see what we're doing here. Every time we increase x by 1, we are in effect multiplying the function value by another 2. Another 2 each time gets multiplied into the value of the function. So 2 is the growth factor. The answer to this question is really simple. It's whatever the b value is. That's it. Okay? And this is true whether this is a growth function or a decay function. That b value, that's the growth factor or the decay factor. Okay? What is the domain? Well, I said earlier that these functions have no vertical asymptotes. Okay, so this function is going to keep on going out to the right forever. There's no border, there's no boundary, there's no fence holding it in. Clearly, it seems to be going way out towards negative infinity that way. Okay, so the domain all the way from negative infinity and all the way out to positive infinity. Remember, the domain is the x values or the input values. And if you look at this expression here, 2 to the x, there's nothing that we couldn't put in for x. We could put in a billion for x. 2 to the 1 billionth power would be a crazy large number, but it would be a number. It wouldn't be undefined. Okay, and we can put in 2 to the negative billion, or let's take a slightly smaller number, negative 100. I remind you that anything to the negative power is the same as 1 over 2 to the opposite of that negative power. 2 to the 100th power is crazy large, so 1 over a crazy large denominator is a crazy small value, but it's not 0, right? And no matter how more and more negative that x value gets, in other words, no matter how bigger that number gets, we're going to get a bigger and bigger denominator. But if the numerator is always 1, then that fraction's never going to reach a value of 0. And so there's a little bit of an explanation for you as to why there really is a horizontal asymptote there, and why the range, in this case, goes from, not infinity, from 0 and up to positive infinity. Remember, the range is the y values or the function values. Okay, and they're never going below 0, but we can see that they are heading up towards positive infinity. Okay. This domain, this will be true for all exponential functions. Okay, all of them. The range we can shift with a little bit. Okay, so that won't always be the answer for the range, but the domain is always the same. X-intercept, well, there is no x-intercept. At no point does this graph intersect the y-axis for the same reason that the range does not include 0. There is a horizontal asymptote at y equals 0. Okay, no x-intercept. There is a y-intercept, and we can see it right here. I had Desmos show us the y-intercept clearly. But again, we don't really need Desmos to show us this. We recall that to find the y-intercept, you plug in 0 for x. So f of 0 would be 2 to the 0 power. Maybe you haven't seen anything to the 0 power in a little while, a couple of months, so maybe you've forgotten. But anything to the 0 power is equal to 1, whether it's 2 to the 0 power, 3 to the 0 power, 5, anything to the 0 power is 1. Okay, so we don't really need the graph to show us that. Decreasing interval, okay, over what x values from where on the left to where on the right is this function decreasing, going down, and where are the y values going down, down, down? Well, they're not going down anywhere. Okay, so I opened up an interval to write in the answer there, but the answer is there is no decreasing interval. These y values are always, always increasing. Way over here on the left, they're not increasing by much as you go to the right. They're increasing by little, by little, by little, by little. And then at some point, the amount of increase starts to accelerate very quickly. Right? So the increasing interval is all real numbers. Okay. Now, these two answers can be switched. They will be switched if we're looking at a decaying function, a function whose values are going down constantly instead of going up constantly. We'll see that in the next example. Okay. And then the end behavior, well, now that we've answered all of these other questions, we basically have our answers to end behavior. As x goes towards negative infinity, as it gets more and more negative, as we're going in that direction, the y values keep getting closer and closer to 0. But as the x values go in this direction, the y values are getting infinitely large. Okay. So again, you've answered almost all of these types of questions before. Questions 3 through 9, you've answered all of those kinds of questions before. Questions 1 and 2, you haven't answered before, but they're fairly simple. But the key things that you need to know to answer a lot of these questions correctly, again, is the fact that yes, there is a horizontal asymptote for all exponential functions, but no, there is no vertical asymptote ever for exponential functions. Okay, there is a horizontal asymptote, and I should draw that as a dashed line, really. But there is no vertical asymptote. Okay, if you know those two things, then you can answer all of these questions correctly. Okay, now here is an example of a decaying function. Okay, it's decaying because the y values, as we move to the right, forward in time, the y values of this function keep getting smaller and smaller and smaller. What is the decay factor? It's always the b value. Whatever that b value is, that's the growth factor or that's the decay factor. Okay. The domain for all exponential functions is all real numbers. The range, in this case, again, goes from 0 up to positive infinity. Again, we can move these functions, and we will in the next lesson, probably in the next lesson, we can move these functions up or down a little bit, and that can change the range, but it's not going to change the domain. We don't change the domain even if we slide this function to the left or the right. That doesn't change the fact that the domain is all real numbers. Okay. The x-intercept, again, there is none. And again, these two answers are what they are because there is a horizontal asymptote at y equals 0. Okay. Now, again, that horizontal asymptote, that can shift. We can shift that, the whole function and the asymptote up or down a little bit, but there will always be an asymptote. Okay. The y-intercept, again, is at 0, 1. If we put 0 in for x, what's f of 0? It's 1/5 to the 0 power, and anything to the 0 power is 1. So this goes through 0, 1 again. Now, again, we can shift this whole function up and down, left and right, so it won't always have a y-intercept of 0, 1. Okay, but in this case, it does. The decreasing interval, well, the y values in this function are going down all the time, right? They're always going. So the decreasing interval this time is from negative infinity to infinity, and the increasing interval, well, there is none this time. So these two answers are exactly reversed from the way they were in the previous problem, okay? And then the end behavior is essentially reversed also. As we go towards negative infinity, as we get more and more negative, the y values get higher and higher, positive infinity. And as we go in this direction, as x gets infinitely large, the y values are getting closer and closer to 0. So these two answers were flip-flopped from the way they were in the previous function. Okay. I want to take a quick time out here and show you my Desmos screen. Oh, I'm not showing you this on my all right. Well, it's not entirely necessary that I show you that. Let's move ahead to the last couple of questions. There are going to be 2 questions like this one on the homework tonight. I'm going to show you a graph and ask you which of the equations corresponds to that function. Now, if you use your graphic calculator or Desmos and just start putting these equations in one at a time, you'll see right away that these 3 don't look anything like this, because these 3 are all growth functions. They're all going to be going up from left to right. But hopefully, without even graphing these, you would know that because these b values, the 2, the 3, and the 4, they're all bigger than 1, y values keep getting multiplied by, a number like 2 or 3 or 4, which is going to make the y values bigger and bigger all the time. Growth functions go up from left to right, and decay functions go down from left to right. This is going down from left to right. It's got to be a decay function. It has to have a b value that is smaller than 1, because again, every time we increase the x value by 1, that means we're multiplying by this b value another time. And if you multiply something by 1/3, the result you get is actually less than what you started with. That's what's making the y values go down. But you could graph all of these functions in Desmos, and you might have a hard time distinguishing one from the other. They're going to look a lot like each other. Okay. But I have given you a clue here by giving you the coordinates of one very specific point also on this function. Okay, so we could plug the coordinates of this point into these functions and see which one makes them true. You probably have a suspicion that it is this function here because of the 4 there and the 4 there, but let's try it. Let's plug in -1 for x. F of -1 equals 1/4 to the -1 power. Now, what is 1/4 to the -1 power? Well, that's going to be equal to 1/1/4 to the positive first power. Okay, that's just basic rules of exponents. 1/4 to the first power is 1/4, so that simplifies to 1/1/4. Now, how do you divide a number like 1 by the fraction 1/4? You multiply the number 1 by the reciprocal of 1/4. 1 times 4/1 is equal to 4. So f of -1 does in fact equal 4. And that confirms that this is the equation that corresponds to our graph there. Okay. So that's it. Like I said at the start of this lesson, many of these questions you could answer, or if not with absolute confidence, with some confidence, you could answer these questions correctly. The key thing again to know is that they all have a horizontal asymptote, which in the next lesson is going to move up and down on us a little bit, but they never have a vertical asymptote. The domain of exponential functions is always all real numbers. Okay? So that's it. Good luck on the homework.